So the way the class is scheduled, the way I'm planning on scheduling the class, well, no, the way it's scheduled. Spring break next week, which is nice. And then when we come back from spring break, there'll be a series of 4 guest lecturers, 3 of whom are going to be talking about empirical applications of stuff that we've covered, including maybe instrumental variables and different differences, mixed effects perhaps, regression in general. The 4th is Chris Dubner from CHOP, who gives a nice inspiring sort of Ruby-like talk about secondary data in his career. And then we've got 1 week of kind of a bridge week before class presentations start. I already know I'm going to be out of town for one of those days, so I may be out of town for the other one. So it's looking like this is it. At least potentially this is it today for me, having the whole class to talk to you about the things that I want to talk about. And I want to talk about instrumental variables. But before I get started, any questions on anything so far? Mechanics, organization, existential, ontological, whatever. Okay. So I want to talk a little bit about the Stuckel paper. Actually, not as much as I thought I might, and then shift into showing you how to implement an ID analysis, supposing you're actually able to identify a plausible instrument. And then I want to conclude with some technical aspects of instrumental variables. So if we only get this far, which I think we'll be able to get at least this far, then the technical aspects you'll need to read on your own. The reality of instrumental variables is that the state of the art is moving rapidly. So what I'm trying to give you in 160 minutes or so is, Tuesday was sort of the conceptual underpinnings, and then today, by the end, you'll have seen the state of commands to actually implement a basic instrumental variables analysis. This doesn't mean it means you could go off and do your own instrumental variables analysis, but it probably also means that to get the technical aspects right, you'll probably want to do some more reading, consultation, whatever. Instrumental variables is the kind of thing where in a 12-page grant, you can have 1 sentence or 2 sentences about, and also we're going to do instrumental variables analysis. You can also have pages and pages and pages of complex mathematical equations and justifications, if you're into that kind of thing, saying, well, this approach is better than that approach. So I'm giving you probably the important 80% of what you need to know, realizing that when it comes to time for actually implementing this thing, state of the art has moved a lot. The cutting edge stuff is ongoing, and so we learned 2 stages of squares. 2 stages of squares is what we'll talk about today, is like a solid. It's like the AK-47 of instrumental variables, right? It's widely used, it's reliable, it doesn't break down kind of thing. But it's not the shiniest, fastest, newest, super technical thingiest of us all. So, I wasn't ever going to promise to make you experts at anything. I'm barely, don't even know if I'm an expert myself, certainly not instrumental variables. But after today, you'll know enough to go out there and give you enough rope to hang yourself with, instrumental variable wise. The rest is up to you. So that's my preface. AK-47, enough rope to hang yourself. Okay, good, we got that. So just for those of you who weren't here on Tuesday, or just to make sure we're all on the same page, just the basic intuition about an instrumental variable. It's this magical silver bullet kind of thing, we'll call it Z, that serves to pseudo-randomize the assignment of the values of the treatment across patients. And it must satisfy 5 conditions we talked about, but these 2 are of particular importance. The relevance condition, which says that the instrument must be correlated with the treatment. Here I'm using X, I really should be T in most of my other slides. And it should not be otherwise correlated with the outcome except through the treatment. So those are the key aspects. If you can find that magical bullet, like the example, the greatest example I used, the best example I used on Tuesday was the idea of randomization assignment in a trial as an instrument for whether or not you actually got the treatment. It's perfectly correlated. It's not perfectly correlated. It's highly correlated with whether you get the treatment, but it shouldn't otherwise be correlated with what your outcomes were except that treatment, whether you the treatment received. And then awesome pictures, Ghostbuster style. So this is our instrument, Z. It should be correlated with X. X may have some reverse causality with the outcome Y. There may be some observed and or unobserved confounders, W, which are influencing both treatment status and outcomes. Z works through X, is not allowed to work through anything but X, and if you get Z to work through X and nothing else, then you could identify the red line being the causal effect of X on Y, the treatment on the outcome. Again, if this is all you learned in those first two slides, then I consider my job, this exposure a success. How we interpret the results of our instrumental variables analysis, the key issue with respect to interpretation is who are the patients who are the subsample of subjects, I usually call them patients because that's the way I talk about them, that are actually affected by the instrument. So in a trial, you've got a nice situation where everybody, you're comparing the average of the treatment to the average outcome of the control. There's no doubt about randomization affects everybody. It's neat. It's overall the average treatment effect is the average treatment effect for everybody. In an instrumental variable analysis, you're identifying something potentially different. That is, you're really identifying the causal effect of the treatment for those whose behavior or those whose receipt of treatment was influenced by the variation in the instrument. So think about the cath example again. Some people live far away from cath hospitals, some people live close to cath hospitals. The treatment, so of those patients, some patients are always going to get cath no matter where they live. Some patients are never going to get cath no matter where they live. The instrumental variable analysis using distance as an instrument for whether or not you got distance to the closest hospital with a cath, as an instrument for whether or not you actually get cath on admission with an MI or something, is applicable to those patients for whom their treatment status was affected by whether or not they would have gotten cath if they would have gotten cath if they lived close, but in an alternate universe if they lived far away, they wouldn't have gotten cath. It's a pretty hard population to identify. Arguably, it's impossible to identify. We don't know who those patients are. The data, I don't think there's a variable in our data set that says, oh, kind of would have gotten cath if they lived closer. Not usually a kind of a clinical indicator. Shouldn't be by construction of our instrument, right? Our instrument should be correlated only with receipt of treatment and not outcome, so it shouldn't be influencing whether or not they got the treatment, except for the fact that they lived close or not. So that, this is called the local average treatment effect or the marginal average treatment effect. And the key point is that it's a function of exactly the instrument that you're using. So if you have two different instruments trying to identify the same treatment, randomizing patients in a pseudo fashion to whether or not they get the treatment, one instrument could be distance, okay? They live closer or farther away. Another instrument could be something else that has some variation in it. Though the causal effect that you're identifying is a function of, is kind of unique to that particular instrument. They may be the same, they may be different. If they're different, you're not sure if it's because the instruments are good or bad, or because they're identifying different local average treatment effects, which is kind of another somewhat more insidious feature of instrumental variables. I mean, that you have to take this, you have to say, okay, in this analysis, I've got this local average treatment effect. It reflects causal effect for this particular subsample of our population. Is that generalizable? I don't know, but look, it's a big number and significant. Please publish my paper. I'll show you this in kind of in an example as we after we get past the Google paper. So this is an important piece. When someone says this is my causal effect, I use the instrument variable analysis. This is my causal effect. It's a causal effect conditional on what the instrument was that was chosen. Important thing to remember. All right, so let's talk about Stuckel a little bit. Maybe some of you at least glance at the paper. That would be great. So I don't know if there's room anymore for another paper in JAMA comparing the outcomes of propensity score regression, regression analysis, propensity score control, propensity score matching, and instrumental variables. So this, maybe one of those papers that's like, wow, in 2007 this was publishable, and then kind of sucked all the air out of the room. Since then, there have not been a lot of IV papers in JAMA. I don't want to say this is because of Stuckel. Well, there could be two reasons. One is the Stuckel paper kind of did it. So, if you want to go for the, look, methods comparison paper, This is an easily well-cited paper, and unless something substantial has changed about why IB is better or different, or kind of the newest stuff, then probably JAMA's not going to be that interested. But also the conclusions from Stuckel, which we'll get to in a second, were important, but also not necessarily like, oh, IB, they were circumspect. IB is not so awesome after all, right? So the story, the context for Stuckel and company was they wanted to look at risk-adjusted mortality as a function of whether you got cardiac cath. Following on another JAMA paper that was even more groundbreaking by Mark McClellan and Joe Newhouse and Barbara McNeil at Harvard back in 1994, the first application of instrumental variables in clinical literature. Came from Harvard, well done. This was the first paper using differential distance as an instrument for whether or not you got cardiac cath on admission for MI. Stuckel comes along and says, somehow, I'm actually going to publish another paper on this. I'm going to use a different instrument. I'm going to wait 13 years to do it, and I'm going to set it up in the context of doing some comparison. So it's a familiar application of instrumental variables even in the clinical literature. The data, so some reasons why the results might have changed. Well, McClellan and company did it in 1994. Stuckel used same kind of data, Medicare fee-for-service claims, but on a population 10 years later in time. So maybe the actual causal effect of cath and mortality post-MI had changed, but that really wasn't what the story was about. I think it was more, this is just how does IB line up with these other methods for trying to go after causality. So they, why not simply regress whether or not mortality on whether or not you got cath, controlling for other comorbidities. So they do that in 3 different ways, at least. They do kind of multivariate regression adjustment, they do propensity score, and then use propensity score as a control, and then they also do propensity score, I think, matching as well, and come up with another version. All these are around, they find a relative mortality rate of around 0.5. So cath post-MI is related with a 50% reduction in mortality. I think it was 30 days, I don't remember what the time frame was off the top of my head. But the 3 techniques all agree with each other. And so one conclusion might be that's really reassuring, right? We did 3 different ways and we got the same result. A more cynical conclusion might be, well, you did 3 different ways, but you're controlling for the same variables, right? So is this really like, it's like heads I win, tails I win, tails you lose, right? Like, did you really actually do anything different? But, and I'm not accusing Stuckel of anything yet, I just said we did 3 different ways, we got comparable results. That shouldn't be too surprising. We're controlling for essentially the same information across the different techniques, that is, the things we can observe ahead of time in the Medicare data. So, all right, now that sets up is IB different? And so, to do IB, you have to have an instrument. What is a good instrument for predicting whether you got a cath on admission, but not otherwise correlated with your outcomes for MI? Could have used differential distance. Not actually sure why they didn't, except maybe they wanted to be different enough from the McClellan paper to try to get in. For whatever reason, I mean, these aren't bad reasons, but they use a different instrument. They use regional cardiac catheterization. So
that's their own thing in Dartmouth too, right?
I'm sorry?
Like regional rates of things that's their bag, so they wouldn't use their bag.
Yeah, that's right. Yeah, right. Use their bag, maybe. Use my bag. Right. So right, because the 2 of the big authors are from Dartmouth. I think Stuckel's got some appointment with Dartmouth or something, even though she lives in Canada or something like that. Anyway, so their instrument was regional catheterization, right? And Dartmouth is well endowed with Medicare data, and they've already divvied up the country into these health services areas and health referral regions, and so they could easily say, like, okay, let's put every hospital in. Well, we use our already existing work and say, let's, every hospital's already been assigned to an area, and every zip code's already been assigned to a market area, so we can just line this up and count catheterization rates. Count the number of MI patients in the market and use that as a denominator, and then the numerator is the number of them that got cath on admission, and you got the easy rate right there. So they do that, and they find actually that the measured effect of cardiac catheterization mortality becomes much less large, much smaller, right? So before it was a 50% reduction in mortality, now it becomes like a 16% reduction in mortality, controlling for the same X's, the same observables, but now also using the instrumental variables approach with cardiac catheterization. So is this a good instrument? Well, the two main criteria are relevance and exogeneity. Is it relevant? Does regional cath rate is it positively correlated with individual patients' probability of getting cath? Yes, it is. I mean, I can't remember if they used lags or not. They probably should have. You'd think it kind of is by construction a little bit. So there's some like, well, are you setting it up to win? But that's fine. Like, of course it is. You live in an area with an intensive rate, you're more likely to get it. That makes sense. The exogeneity criteria, though, may be a little more squishy. Is the regional cath rate related to individual mortality only through the receipt of cardiac catheterization? Are there potential other mechanisms that might be working, or maybe, is it possible that the cath rate actually has a direct effect on outcomes as well? So some concerns with the regional treatment rate as an instrument for did you get cardiac cath or not. One is, are the regional treatment rates correlated with patient factors? Well, so if they're correlated with patient factors that you're controlling for, not a problem, because you're controlling for them. So you're purging the instrument of that influence. You're saying these sort of unique variation, but that instrument is still explaining whether you got cath conditional on X's that you can observe. But if there are features about patients that lead to, so Boston has a high cath rate. It also has particularly sick people in ways that we can't measure, and those particularly sick people are also more likely to die. Then that would be a problem for using regional cath rate as an instrument, right? It's violating that exclusion restriction. It's saying that there's something else going on here through the mechanism of patient severity that is, that the cath rate is working, a regional cath rate is working through. There's another story that's a little more subtle that may be a threat, which is this idea of specialization across markets. So specifically are the markets in which there are high cath rates actually the markets in which people are really good at using cath. That may not be a problem in the context of a treatment where provider quality really isn't relevant. So like, think about prescription drugs, you prescribe it or you don't. That's a nice, like the mechanism is all in the pill. There's no quality aspect of like that I prescribe it really good for you. And because the way I prescribe it, is that leading to your quality. For cath, I don't know clinically whether, operator or some sort of, there's some sort of idea that you can be good at cath.
It's a huge deal. Yeah.
Well, I just don't know. I've never done it before.
It is a big deal.
Okay.
You don't want me doing your cath. I'll tell you that much.
But so looking at people.
No, it's different for sure by region.
Okay. All right. Then you've got a potential problem right there with regional cath rate. And as you move up the complexity of surgical interventions, it's not hard to think that this specialization story becomes more relevant. They're really good at doing it in Minnesota because, well, Mayo's there and they attract really good people, and that, so that might make regional. Both those things might make regional treatment rates suspicious as instruments. But then the other piece, which is, so that violates the exclusion restriction. I think the comeback to that, which the Dartmouth people, which Stuckel and company at least would argue for, is that, well, we're not really measuring the causal effect of getting cath, just getting cath, narrow sense of did you get cath or not. Everything else that happens to you is the same. We can't observe all that in Medicare data. What we can observe is whether you got cath or not. But what that's really standing in for, the treatment is, did you get cath plus a whole host of things that happens to you when you get cath. That's sort of like a package. The package of cath plus downstream things that also might influence your outcomes. And so it's not, it's not that protects them against either of these specific concerns, but it may be that this is sort of an argument to try to ameliorate the generic concern of are we violating the exclusion constriction. So it's not so much that if we're saying, okay, here's our guy again, right? We have, We've got Z up here, that's our instrument, treatment here, outcomes here, right? So we want to make sure that that's the only pathway that's really going on. What if there's some other stuff up here that Z is working through? If that other stuff that we're not capturing is really part of the cascade of CAF things, then maybe it's really like, it's not, we just need to reimagine what the treatment is, right? So it's not, the exclusion restriction is not just did you get CAF, but did you get CAF and CAFy things up here in this cloud? We may be okay with the exclusion restriction. In other words, we need to think carefully about what our treatment is really representing here. Regardless, I don't think this has anything to do with patient characteristics, which are clearly kind of a violation. Okay? And they're probably not also related to specialization, like are you getting CAF in a good place? So the first two concerns, I think, are still totally legitimate concerns about the use of regional treatment rates on, regional CAF rates on MI mortality. Okay? So I want to move on from there. But so that was one set of concerns about, is the exclusion restriction violated using regional CAF rate? And I think there's reason to think that it is. Of course, I can't prove it, right? I mean, I don't, well, maybe the ways to go out and fetch data that suggest that these are issues, but it's not clear how you would measure quality of CAF necessarily, or maybe you can. I mean, maybe there's good ways to do it. Another set of concerns is, who is the marginal patient being affected by this particular instrument? So we've got regional CAF rates, right? So we're talking about not the people who would have gotten CAF no matter where they lived, not the people who would have gotten CAF, who would not have gotten CAF no matter where they lived, but the people for whom, if they're in a high-intensity market or a high-rate, high-use market, would get CAF, compared with the same person who was somehow transported to a market in which the CAF rate was low. That is, the marginal patient is one who, by moving markets from low to high use, would then go from not getting CAF to getting CAF. Not only is that a hard, if not, again, possibly impossible subsample to identify in the data, to say like you are not one of these patients at risk, it also raises the question of so what? So you found a causal effect. Do you care about the subpopulation that you're talking about? Is this the subpopulation of patients that we can do anything about? Like, is the policy proposal that we should shut down CAF and maybe there's a regionalization story, and so it's like, okay, if we, maybe it is possible that we shut down CAF in this market, the CAF, low use CAF is no bother, we're going to move everybody to the high use area somehow. Not exactly a regionalization story, but there may be some policy that's relevant here. It's not obvious to me what that policy is. And so you identified a causal effect. It's different from the average causal effect that you found using just control for observables. And so what do you make of this causal effect? Well, they're different. Okay, so I think Stuckel had a totally legitimate conclusion about IV being most useful for identifying policy, for the impact of policy interventions rather than necessarily narrow clinical interventions, although I will say Pecori and comparative effectiveness are totally embracing instrumental variables as a legitimate, and it is a legitimate approach, but nevertheless we need to be very careful about what it is we're concluding from this. What is the conclusion of the Stuckel paper? That the use of CAF really isn't as life-saving as we would think it is based on a typical analysis that only controls for observables. We have highly different estimates, 0.5, 50% mortality reduction, 16% mortality reduction. Non-trivial amounts of mortality reduction, which is the right answer. Knowing again that the 16% reflects an estimate on a population that is possibly, arguably not well identified, but also maybe not policy relevant, but nevertheless may represent something that we care about. So, I don't know, what's the right answer? Is it, we need more CAF? We need CAF, we don't need as much CAF as we think we do?
More CAF.
More CAF. We need fewer cardiologists and more dollars per cardiologist. But somehow more CAF.
The answer only applies to that marginal group?
Well, we don't know. That's who we're identifying the effect of. We don't know the generalizability of that IV. If we had a different instrument, that wasn't, say, regional cath rate, but was something else, we would identify potentially a different latent local average treatment effect. If they're the same, you might think that's suggestive evidence that there's some generalizability. We did it 2 different ways and got 2 different results. I got the same result twice. But in the absence of having a second instrument to sort of check that, we can't say anything with confidence about, I mean, this is the part of the discussion section where you say, we have no reason to think these aren't generalizable, because we have no reason to think that they are either. Like, so, I don't know. What do you think? Publish the paper, please, and let someone else figure it out.
What about the fact that they compared to the outcomes of randomized controlled
yeah.
trials?
Oh, yeah, so they did that, right. But I'm just talking about the narrow sort of like, imagine what we don't have the RCTs, right?
Okay.
And so if you have RCTs, then you can say, okay, we found the same effect that they found on RCT, and that's good, and that's reassuring that we can recover that in this particular case, but there's no guarantee that in the future, it's like we've shown it for CAF, it's a function of the fact that we chose this, we got a result based on, it's not on here, regional CAF rate as the instrument. Does that mean we should always go with regional treatment rate for procedure X is going to give us a replicate of the RCT? I don't think there's enough evidence to suggest that that's right. I mean, maybe that will bear fruit in time, but it just goes back to the general theme of careful, because you don't want to go on a limb and say my IV results say, forecast that the world is ending at the same time that the Mayan calendar switches to its next whatever, and so we need to hunker down and change everything radically, because that's not necessarily what your IV results are showing. At the same time, just because they're, if you get results that are different from the controlled by observables approach, maybe you're getting at actually addressing unobserved selection bias kind of stuff, and so that could be good. So it's just, a lot of it depends on the quality of your instrument and applying the right methods. And the conclusion you make at the end of this is going to have to be one of these, like, on one hand, but on the other hand, not necessarily the most satisfying conclusion, but maybe still better than, well, there may be a omitted variables bias problem, but we don't know, we can't do anything about it, so we're not going to worry about it.
How was maybe the cardiologist could say, why was the findings with the other analyses so much higher than randomized controlled trials?
Well, I mean,
why is it 50% reduction?
So, I mean, I guess it's, just based on a simple statistical story, there are factors that influence your receipt of cardiac cath that weren't controlled for in the straight-up observables as Medicare claims data. They're not comprehensive in a clinical sense. And so there are things that influence whether you get cath or not that are also influencing whether you die within 30 days or not. And so failing to control those unobserved those residual confounding or omitted variables bias, it's going to lead you to a biased estimate in the regular thing. But so enter IV. Great, we have this technique, we have this thing, but it's not a panacea. Again, you have to be careful using this, and not because, like, again, it's not the methodology is going to hurt you, it's that the conclusions that you draw from your results need to be put in the right context. That it's unfortunately a kind of a left-hand or on one hand on the other hand kind of context. Having an RCT to appeal to, great, but that again it goes back to what's your IV and how good is it in this particular case. Any questions?
I guess I'm having conceptual difficulty in terms of if the instrument is supposed to help us account for omitted variables in our analysis of the outcome, but we don't actually know if the instrument is then associated with those omitted variables and have a pathway to the outcome.
Well, so part of it is rhetorical. Part of it is you making arguments about the quality of your instrument. So it's like the, regional variation in cath. Like, what are the determinants of regional variation in cath? Is that truly is that something that comes from the sky? Is it based on weather patterns? Is it based on completely exogenous criteria? Probably not. That makes regional cath use somewhat suspicious already, because you're assuming that it's not affected by anything else going on here, but maybe it is. If it's something like, I don't know, like draft number, something that's got a plausibly random assignment. I mean, ideally, it's how good is your instrument relative to random assignment. And if you could say it's the same thing, then you got a lot better, you're in a lot better shape than if you don't. In the absence of having a perfect instrument then the other strategy is to say, I have two different enough instruments and I get comparable answers, that I have more confidence in what I've done. The single instrument studies are still showing up and probably will continue to show up in medical and health services research journals and PCORI type of ranking stuff because it's hard to get multiple instruments. But in the economics literature, most of the journals have moved away from single instrument studies to say, like, if you're really going to go after your IB, show me two different instruments and show me that if they agree with each other and are different from the non-instrumented analysis. And so, it's context, it's rhetoric, but it's having a bigger evidence base to, apply that to. So there's not going to be an instrumental variable study that's going to be definitive, I think, by nature. So one more nit to pick with Stuckel, scissors clarity, because she got an exam, and I didn't get an exam. I don't have an IDP, but if I did, I'd probably get an exam. They had this thing, I just take some issue with the level of clustering. So they do account for the fact that patients are nested within clusters within hospitals. That's good and all. But in reality, the instrument is at the what level? At the market level. So they probably should be counting for the fact that patients are nested within hospitals, the hospitals are nested within clusters, so that there's this fewer degrees of freedom feature to their analysis than they're actually accounting for. What would that do? That would only change the confidence interval. Not going to change the point estimates whatsoever. Not a big deal. Like I said, it's a nit to pick. But if I were reviewing this article, I would have said something about it. They would have fixed it, and that would have been that. I still would have. It wouldn't have kept them out from clearly. All right, so that's Stuckel. That's a published paper. Let's see what we can do with some of our own data. Well, let me walk through the basic methodology, which is called two-stage least squares, and show you some examples, and then build it up in increasing, not complexity, but increasing from simple to less simple. All right, so our basic approach with IV is going to be basically to replicate this two-stage process. Instrument affects treatment, treatment affects outcome. But we're going to do it in data. So we're going to wind up regressing. This is two-stage least squares in a nutshell. We're going to wind up regressing. Our treatment is an outcome. It's our first stage as a function of the instrument. And if we have controls, we would put the controls in this stage as well. So we're going to use that regression to generate t hat. That's the prediction from this model that gets sort of as a function of whatever controls we have in there and the instrument. That's how we're purging Z. We're purging T, the treatment of everything, and just leaving it with just this Z, the influence of Z on T, left over in T hat. Take that T hat, and now instead of regressing Y on the treatment, we're regressing Y on the predicted value of the treatment. If this is a binary treatment, it would be a predicted probability between 0 and 1. And basically that's it. Then our estimate of this coefficient B is going to be the causal effect of the treatment on the outcome. Again, the local average treatment effect. But it's only going to be consistent. It's not going to necessarily be unbiased. It's also going to have larger standard errors than the same estimate would in ordinary least squares regression. The larger standard errors issue is kind of annoying, not annoying, but it's unfortunate. This consistency process, though, is saying, okay, if we have a large enough sample, which is another piece of the IV argument, we have to have large samples to use IV, because this is what's called an asymptotic argument. This is, as the samples get large, B gets unbiased. In small samples, the performance of IV much less reliable, and there's a lot of work going on in small sample properties of IV. But if you've only got 10 subjects, or there's no magic number, you want as many subjects as possible, which is maybe why, in the context of comparative effectiveness research and so on, having large administrative claim databases is actually a good thing, because you need large data to get to be able to appeal to this consistency of IV. Now again, there's not like a magic number, and so whatever data set size you have. If you use IV, it must have been large enough, because if it wasn't, why would you have done IV? Of course, right? I mean, so, it's not, I don't have any rules of thumb for you on this, except large enough is good, without telling you what large enough is. So how do we implement this two-stage process? It's called two-stage least squares. It's the easiest way to do it. And again, so it's the same thing over again. We have our dependent variable. This is our estimating our equation of interest, right? What's the effect of the outcome of the treatment and controls? However, this treatment variable is what's called endogenous. We talked about that a little bit on Tuesday. This idea that it's influenced by other factors that we're not potentially controlling for. All these other W's are assumed to be exogenous. That is, that they're not endogenous, they are what they are. The kind of things that may be time immutable, they're not affected by omitted variables bias. They would be, if we took out T, the equation Y on W would be fine, right? These are things like risk factors or age or sex, or just things that aren't going to be influenced by something else, like say whether or not they got treatment or whether or not there was a policy in that state. And then so we estimate this same equation as again, treatment as a function of our instrument, and then outcome as a function of our predicted treatment. T hat is the predicted treatment. And what we really want is this lowercase b. That's all you gotta do. I mean, it's simple as that. Once you get an instrument and then go run two-stage least squares. So why not regress y on the instrument directly? Why not just bypass t and say, all right, take t out, what's the effect of z on our outcome y? So if we do that, we have, again, not controlling for other confounders, but we could add w to the model, no problem. Treatment is a function of beta z, y is a function of bt. If we put the formula for t into the second equation, we realize that our outcome y is now, the coefficient that we're estimating is actually the product, lowercase b times beta. That is, it's both these things, but we really just want lowercase b. We want the causal effect of treatment on outcome, not the causal effect of treatment on outcome, times the effect of instrument on treatment. Not that you would ever have thought that you should have regressed y on z, but this is why we don't do y on z. But here's a little trick, right? So if the outcome of this, what's called reduced form regression, that is y on the instrument, is b times beta, this actually leads to this idea that we can divide b times beta, the outcome of this, by the first stage regression to get b here, beta, and divide b times beta divided by beta to get lowercase b. That is the Wald IV estimator that I talked about on Tuesday. So two-stage least squares and Wald are actually the same thing, except with two-stage least squares, you're able to now start controlling for confounders. So two-stage least squares, I just told you, first stage is treatment on instrument, second stage is outcome on predicted treatment. Here's our reduced form regression. Outcome on instrument. Again, now we're controlling for W's. So I told you the Wald regression, Wald IV estimator was in a simple context of no covariates, just have means of outcomes and whether or not kind of what your treatment status was and what your instrument status was in a binary instrument kind of way. So whether you were randomized to this group or that group is a binary instrument. And so we're taking, in the Wald instrument, we're taking, this is effectively a reduced form regression, the difference in outcome when your instrument, when you're randomized to get the treatment, minus the difference in outcome when you're randomized not to get the treatment, divided by whether the rate at which you actually got the treatment, conditional on being randomized to it, minus the rate at which you actually get treatment, conditional on not being randomized to it. It's the same thing as saying, oops, I forgot a little, there should be another beta there. B times beta, which, capital B, that's the reduced form outcome, divided by beta gives us our lowercase b thing. That is essentially two-stage least squares and the Wald IV are doing the same thing. They're looking at our reduced form, our intention to treat analysis. What was your outcome conditional on what you were randomized to? But then accounting for rates of differential rate of non-compliance in the same way as the wall IV did in that example on Tuesday. Oh yeah, sorry.
So W is all the things besides the instrumental variables?
W is all our other confounders.
Like
W is-
patient-wise and like the hospital?
Yeah, whatever else we're controlling for, it could be empty and we're not controlling for anything. It could be, you know, in the context I'll show you, in the drug-eluting stent context, it could be, you know, raised payer, comorbidities, blah, blah, blah. But whatever else you're putting in the model that you're controlling for, you normally control for, used to control for differences in outcomes.
So why is that called exogenous?
Well, it's not, we're assuming it's exogenous. We're saying it's not. The problem with the causal effect of the treatment, right, is that there may be other factors that are influencing treatment that are also influencing outcomes. For any of these other W, any of the elements of W, like, you know, diabetes, does the patient have diabetes or not, right? That's not being caused by, that's assigned to the patient by virtue of, you know, in the context that we're talking about, you know, it's something that was realized, a realized outcome of a process that is separate from the regret, separate from this whole conceptual framework of does getting drug-eluting stent lead to whatever we're going to look at, or does getting a cardiac cath lead to mortality. It's out here in space. It's not affected by the instrument. It's also just, does the patient have diabetes, yes or no? We're controlling for it. It may influence whether they get a stent or not, but in itself, whether you have diabetes is not something that's mutable. Well, not in the sense of mutable in our particular conceptual framework, right? It's outside the conceptual framework. Or it's not, it only affects the outcome. Nothing's affecting it, is the point. It's not being caused by anything else in the conceptual framework. Whereas whether you get a drug-eluting stent or not is being caused by something else in the conceptual framework, but we can't control for those things that it is being caused by. All right, so how do we actually do two-stage least squares estimation? Well, there's two ways we can do it. We can do it the manual way, which is at the first stage you run an ordinary least squares regression, regardless of whether treatment is binary or continuous. So that our dependent variable here is treatment status, but treatment status could be binary, it could be continuous, it could be positive, whatever it is, it doesn't matter. Run OLS. Then the second stage, run OLS again, using t hat from the first stage, and you get your result. The coefficient is accurate, but the standard errors are not right because we need to adjust them for some technical issues. So we can do it manually, but nobody does because these estimators, two-stage least squares estimators in all the stats packages, including Stata, and it'll take care of the standard error adjustment for you. So the command in Stata is IV regress, and there's a whole number of options to do it, but if you ever want to run IV analysis in Stata, IV regress is an obvious place to start. There are some more sophisticated, even more sophisticated packages that do it. IV regress it is the place to start. So let me run through an example now using my favorite drug-eluting stents, and I don't have a really great outcome for sort of patient clinical outcomes, so I use total charges in the hospital setting. Does whether you get a drug-eluting stent influence expenditures, or total charges are not really a great measure of actual resource use, but maybe they're somehow roughly correlated with resource use. That's all I had. I was starting with length stay. I just wanted to see, does when you get drug-eluting stent versus bare metal stent affect total charges? It's a causal story we're going after. Okay, so let's run through our potential options. So first off, we can just run simple bivariate regression controlling for nothing. What is the difference in total charges by whether you get drug-eluting stent or not? This regression will tell us that. The coefficient is $971. People with drug-eluting stents, on average have charges that are close to $1,000 higher than people who get bare metal stents. Standard error on that is $72. Note, I'm not doing any funny standard error adjustments in any of these things, not because we shouldn't, but only because I want you to see what the relative sizes of the standard errors are without any monkeying around with corrections or adjustments or whatever kind of stuff. So then, control by observables. Stuckel, whatever else we talked about, let's control for a bunch of stuff. And I remember I've had a pre-specified set of independent variables that I've controlled for. I don't list them all here, but there are things like patient race categories, patient payer categories, counts of electronic comorbidities, year, state, a few other things maybe. Admission source, whether you admit on the weekend or not, and we just regress total charges on DES controlling for these things. We find that the estimate, the difference, rises substantially, significantly. Now, if you get DES, your charges are about $3,000 higher on average than patients who got bare metal stents, controlling for other factors. Got much larger, standard error didn't get much bigger. Is this the right answer? Well, we can keep going, right? I mean, we could stop there, but since this is a pedagogical exercise, we're going to keep going. Let's introduce an instrument. So, Stuckel used regional rates of, regional cath rate as a instrument for whether you got cath on admission. Take that idea and go one step further and say, let's use whether the cardiologist's DES use rate in the quarter prior to your stent procedure. You know, doc, you think that there's a high, there's high variation across docs, and some are like go-getters and are much more likely to adopt stents early. Some are low users and skeptical. Not that many though. But there's also a lot of variation over time. We've got data covering from 2003 to 2011, so there's a kind of a big up curve, big adoption, flat plateau, drop, and then resumption that I think I've showed you in the past in drug-eluting stent. So there's lots of variation in drug-eluting stent use, and we're going to use your physician-specific value from the last quarter. It should be correlated with whether or not you as a patient get drug-eluting stent. It turns out it is. I'll show you. Is it also not otherwise correlated with total charges, though? So here's the problem. Docs who use drug-eluting stents may also do other intensive things that lead to both, whether you get drug-eluting stent, but also lead to other things that may lead to higher charges. I don't know what they are, but is this a story about the cloud of drug-eluting stent is really sort of drug-eluting stent and related things? Or is it kind of off the cloud and like, well, they're also just simply, you know, that has nothing to do with whether you get a drug-eluting stent or not, but the docs who do drug-eluting stents are also docs who treat very intensively. Whatever that means in the context of drug-eluting stent, I don't know. Maybe it's not the best instrument, but I'll use it because it's in it for example. You may want to take these results with a large grain of salt. So here are the two-stage least squares in sort of variable results. I first do the naive, or the manual method of computing these results. So that's the first stage of regress DES on the instrument, which I'm calling doc DES and our independent variables, and then regress total charge on this DES hat. That's the prediction. I didn't show you how to get the prediction, but it's actually really easy. The command is predict. And the same independent variables. This says patients who, you know, comparing a patient of a doc who had 100% use rate in the prior quarter with a doc who had a 0% use rate in the prior quarter, 64 percentage points higher to get a drug-eluting stent use if your doc was a 100% user of drug-eluting stents in the prior period. This is a standard error, it's tiny, this is highly significant, so we meet the relevance criterion straightforwardly. And then we get a result, though, of the causal effect of drug-eluting stent use, of getting a drug-eluting stent on total charges is now close to $9,000. But it's the local area treatment effect, right? So this is talking about docs who are patients who would be shifting across docs. Maybe that's plausible. Maybe it's relevant. It's different from what we had before. Now I'll show you the syntax for the easy IV, which is two-stage least squares in the CAN procedure. The syntax is a little different because we're combining both the first and second stage in the regression. The command is IV regress. We ask for two-stage least squares. There are a couple different options. There are variations on the two-stage least squares. The fundamental structure is the same. Dependent variable is total charge. These are all our exogenous controls. And then here's our first stage. Drug-eluting stent is being instrumented for by this doc_DES is the name of the instrument, same instrument as before, and we get the same estimate of the coefficient, and you realize I could have just pasted those, so I can't, that's not sufficient proof necessarily, but I have given you the data set, and now you have the syntax. You could go off and replicate. I'm happy to post the code, and you can go off and replicate it or do it yourself. In any event, the point is you get the same estimate, close to $9,000. What's different is the standard error is much larger. In the bottom one, the standard error here is $257. Up here, it's only $108 because we didn't do the correction here. We did it manually. There is a correction. I don't know exactly how to do it off the top of my head. I wouldn't bother learning how to do it. I would just use two-stage least squares, and it does it for me. Now, if we do the reduced form regression, which is regress total charges on the instrument, not on actually whether you got a DDS, but your physician's use of drug that extend the prior quarter and our independent variables, we get an estimate of 5681. If we divide that 5681 by this first stage 0.64, well, damn if we don't get 8876, which is awfully close to 8830, and the only reason they're different is because I just rounded off these estimates. So if I hadn't rounded them off, I would have gotten 8830 exactly. That was my point about two-stage least squares is walled IV controlling for controlling for other confounders. So we could stop here and say, okay, we did our two-stage least squares. We've got estimates ranging from $1,000 to $3,000 to $9,000. But wait, there's more. So I realize we haven't covered nonlinear models in this class much at all by construction. We'll talk a little bit about logit, but the reality of the world is that Tim's going to be teaching you nonlinear models. Lots of people use nonlinear models for other things. Statisticians and epidemiologists like nonlinear models. And so I want to draw your attention to how to implement internal variable analysis in the context of a nonlinear model. So one option is to ignore the nonlinearity and go back to two-stage least squares and just do linear regression in the front end, linear regression in the back end. There's nothing wrong with that. That's what Stuckel did. Those results are consistent, but they might not be as best as you can do, and you may get pushback from reviewers. And the point is now that we know how to do nonlinear internal variables in a nonlinear context. So the name of the technique is called two-stage residual inclusion, and hopefully that'll become clear why they call it that in a second. It's contrasted with this idea of two-stage least squares, which is an example of what's called two-stage predictor substitution. Predictor substitution means we took the endogenous treatment variable and we replaced it with the predicted value. We substituted t with t hat, our prediction from our first stage model. That's the predictor substitution approach. 2SRI is also known as control function approach, but you don't care about that. What are the steps in 2SRI? They're awfully similar to two-stage least squares. Here you've got a first stage model where t is your treatment variable again, and you're regressing on your instrument and your other confounders. Same as before, except maybe you're not using linear regression in the front end. In the second stage now, your outcome is your outcome, but instead of replacing t with t hat, you leave t in the model and you add on to it epsilon hat from the first stage. That is the prediction of the residual from the first stage. That's the thing that we're doing 2SRI, two-stage residual inclusion. That's the residual from the first stage that we're including in the second stage model specification. So for linear models, 2SRI and 2SPS, two-stage substitution, are the same thing. But for nonlinear models, the good news is 2SRI is consistent, just like two-stage least squares was. But two-stage predictor substitution is inconsistent. So don't ever do this, or not this, don't ever do two-stage least squares, but use a logit in the front end, or use a Tobin in the back end, or use something other than linear regression. If you're going to do two-stage least squares, do two-stage least squares. Don't monkey around with it. If you want to monkey around with it, go to a 2SRI, two-stage residual inclusion approach. There is a cost in terms of complexity, and that is, while we have IV regress that's able to do the standard error correction for us straightforwardly, in the package, there's no packaged version of 2SRI, so you have to do the steps manually. That means you have to do the standard error correction manually as well. The analytic solutions for those are either unavailable or damn difficult. And so the basic approach here is to just bootstrap this process. We haven't talked about what bootstrap is. Basically, the idea is you replicate it 1,000 times, pulling random samples each time, re-estimating the model, and then generating your standard errors empirically.
Andy, if we were doing this as a project and we have all these options, how do we know which one is the best? Like, how do we know which one to choose?
Of the techniques?
Yeah.
So, it kind of depends, right? I mean, so if you want to, you stick with 2 stage least squares. That's safe.
Okay.
Totally safe. And I mean, your best will do it for you. So it's not just like a train, it's the AK-47, right? It's reliable, it's, I don't say indestructible, it's not quite the right word, but it's a safe option. But there's some models that you just can't, that aren't believable potentially in a 2 stage least squares framework, or you just get pushback because you're trying to go to a journal where it's like, but your treatment is binary. And what are you doing using a linear probability model? Well, it's fine, I can give you sites, and you either engage in the frontal, bang, bang, I'm going to argue with you, or you say, all right, I'm going to do 2-stage residual occlusion, and maybe the results are a little bit different, but I'm doing a double logit in the first stage, and I'm doing a Poisson in the second stage, and I get comparable results, so leave me alone. But I've done all this work, so I may as well report the more complicated ones, because it looks like I did more stuff, and that's a good reason for you to publish my paper. So, 2 stage least squares is safe. Some people don't like it.
Okay.
If it's good enough for you, that's fine. It's good enough for me. But I think it's kind of, 2 stage least squares is kind of like 1980s, Car still works, but, we got better technology now, and so we get a more precise estimate. So this is how you would do 2-stage residual occlusion with linear regression. Our first stage model is exactly the same as before. Regress our treatment DES on our instrument. That's the doc lab DES rate. There are a bunch of different variables. We want to predict the residuals, so we say predict DES resid. That's the name of the variable. And we're going to ask for specifically the residuals. If you don't tell Stata what you want, it'll give you the prediction of the outcome, which is not the residual, so you have to make sure you ask for the residuals. And then in the second stage, you say regress total charge, and then we're leaving in the treatment variable, and we're including the residual from the first stage, which we call DES resid right here, and still controlling for everything. Well, goddamn if we didn't get exactly the same answer we got with 2 stage least squares, because we did 2 linear models in the same stage. 8830 is our estimate, and for whatever reason, the standard errors are almost the same. I'm not sure if that's a feature or coincidence specific to linear models. I don't know, but that's linear regression. Suppose we're doing a little bit different, like we're modeling cost data. So a common distribution for cost data is a Poisson, and we have a binary treatment. We have binary treatment. Did you get DES or not? So we want to use a logit in the front end. Okay, so now all we do is change regress to logit, same model specification. Logit's weird because you can't get residuals directly from logit, so you have to actually compute the predicted probability and subtract the predicted probability from the actual 1-0 value to get the residual. That's a feature. And now again, instead of doing linear regression, we're doing Poisson. Model specification is the same. We're modeling our dependent variable as a function of our treatment and the included residual from the first stage and everything else. Because Poisson is a nonlinear model, we want to actually recover the effect size in dollars rather than in log whatever Poisson estimates. So we ask margins. dy dx DES gives me the average marginal effect for getting the drug-eluting stent from this model. And we get something that's a little bit smaller, 7638, but still closer to the 2 stage least squares model than it is to anything else we've seen so far. And much larger than the vanilla Poisson, which I didn't show you, but is there. But we get a standard error estimate of $2, way too small, so we would need to bootstrap that. I'm not going to show you how to do it here. If you ever want to talk about it, I'm happy to. But just know we ran into this, whoa, $2, that's just not plausible, right? I mean, it's not plausible and it's wrong. We know it's wrong. So that's the recipe for two-stage residual inclusion. You don't have to, you can do logit, probit, tobit, schmobit, whatever, like whatever you want up here, and then whatever you want in the back end. Could be linear regression. One of these could be linear regression. They don't have to be. You can do Scooby-Doo regression over here, like whatever you want. And this two-stage residual inclusion is survival models, whatever. If that's what you're getting into, then boom, you're in a two-stage residual inclusion. But wait, there's more. There's more, right? So two-stage residual inclusion is great, but everything we've talked about so far has been in the context of controlling for observables, right? We spent a good week and a half talking about panel data, fixed effects, first differences, and all the benefits that can get. Turns out we can combine our fixed effects estimators and our IV estimators, at least in a linear framework. So here's where we're kind of back in the linear regression world again. Now suppose we add to our model specification, we want to control for hospital fixed effects. We want to control for all time invariant characteristics of the hospital that you're receiving your stent at. Now everything is now being interpreted and identified off of this idea of within hospital over time variation. Even our instrumental variable, which is our physician's lag rate, so that's not, I mean, that's going to be same, that's not really controlling for a lot much, but we're still controlling for all the characteristics of a physician's use of drug stents in the prior quarter that are local to the hospital and time invariant. But also our local average treatment effect is slightly different than it was before. Because now our local average treatment effect before it was switching physicians. Did you from physician A to physician B regardless of where that physician practiced. Now our local average treatment effect is based on samples of patients whose receipt of drug-eluting stent would change based on switching physicians in the same hospital, from one who did to one who didn't. It's a subtle difference, but it may be an important difference. We don't know what impact it's going to have on the model until we actually estimate it, but that's our identification. So we know our identification, we know where it's coming from prior to actually running the model. Then we have to interpret that result in the context of the model we run. So here's our vanilla fixed effects model without any instrumenting. We XT set hospital ID and then XT reg our same model specification asking for fixed effects. We get an estimate of about $3,000 difference, getting a drug-eluting stent associated with a $3,000 higher total charges than bare metal stent. When we combine the two, the command in Stata is XT IV reg. Again, linear regressions on both ends. Similar to the IV regress command, total charge is a function of the exogenous controls, and then we're identifying, or the instrument for our endogenous treatment variable DES is your physician's lag quarterly drug-eluting stent use rate, and we're asking for fixed effects. It's actually very straightforward to get first difference results as well. We get a much larger number than this, $6,000 higher treatment costs, total charges. With standard error, that's also much wider as well, $300, but not wide in an objective sense. But wait, we can do it with hospitals. Why don't we add in physician fixed effects instead of hospital fixed effects? Now our identification is coming from within variation over physicians, over the same physician over time, including our lag change in drug-eluting stent. So this is saying all the variation in your instrument is coming from the same physician as they go up the adoption curve, come down the safety warning curve, and we have a much tighter source of identification, but it's also different from what we had before. Not necessarily better, but tighter. And so the results from this are we're getting the vanilla fixed effects results without any IV, $3,000 difference, and then when we add in the IV, we're getting a over $9,000 difference with a $400 confidence interval. When we put these all together, what do we got? So this is the range of results. Our crude estimate was about $1,000, controlling for nothing. As soon as we control for observables, we get a $3,000 difference. When we control for observables and hospital fixed effects, about $3,000. Observables and physician fixed effects, about $3,000. A little bit different, but by and large, you see the scale. When we control for, all those things are in the $3,000 range. Once we go to an instrumental variable, whether it's two-stage least squares, nonlinear two-stage least squares, linear hospital fixed effects and IV is 6,000, and then doc fixed effects and IV is about 9,000. We get a much larger estimate of the effect. Is it consistently? It's not exactly the same. They're not the same as each other, and the growth from their kind of unadjusted. This is like a $6,000 difference, whereas hospital fixed effects are like a $3,000 difference. So it's not like a standard plus $5,000, not all equal to each other, but you get the sense that controlling for nothing, about 1,000, controlling for observables and maybe hospital and physician fixed effects, about 3,000, and then somewhere between $6,000 and $9,000 from an instrumental variable analysis. Which one's the right one? What's the best one? Which one would you report if it were you? You're like, it's not my analysis, I don't care about this. Why would I write this paper? Which one's the best one? What's the most believable? Or which group of them is the most believable? Who thinks?
I don't know, I'll go out on a limb and say maybe the non-instrumental variables, like with fixed effects.
So, what are the hospital physician fixed
I don't
effects?
know, only because the instrument here was questionable for the reasons we talked about.
But it got better over time, right? That's my argument, is it got better. Like, we're identifying off of less. So we're controlling for, if a physician's intensity doesn't change over time, then we're controlling for it here. But maybe there's an exclusion restriction problem, right? I don't know what the right answer is. Pick a number. It's a good number. It's probably not this one, but is it $3,000 or $9,000? I don't know. Part of the story is, well, they're estimating different things. These $3,000 estimates are applicable to all patients in the sample. These $9,000 estimates are applicable to patients for whom the instrument would change. But it's a potentially compromised instrument. So is it that these are valid estimates for a different population, or that there's bias here, in that, although how much bias we don't know, in that our instrument is compromised because it may be correlated with things related to total charges but not related to treatment, so like that upside pathway? I don't know. There's some storytelling we could do. Maybe the best thing to do, probably the best thing to do, is go get a second instrument that's sufficiently different from, and I wouldn't say use regional DES rate as another. You could, because it's easy, but it's probably too close in some sense to have confidence that we're estimating a different enough effect that it's meaningful. I think it's at least 3,000. I think from in conclusion of our paper, the effect is larger. It's at least $3,000 larger, and it may be more depending on who you are and how good our instrument is. On one hand, but on the other hand. And welcome to the world of instrumental variables. It's nice because you can't get robots to do it yet. It requires subtlety and interpretation and judgment in a way that just kind of pressing the button and saying, okay, regress, doesn't necessarily do. And so maybe those jobs will do this, maybe it was.
Have you published this? Would you consider publishing it? Why not?
Because I don't think the question's interesting.
Yeah.
I think total charges is a crappy, so what? But I showed you a whole, when I use these methods to answer a different question that was readmission rates. I think about it, but I think my forecast, my crystal ball of taking this and saying, okay, let's go to a medical journal and okay, our regular adjustment got this much and our IV got this much. I'd probably say, let's get rid of the IV analysis, or say in somewhere that we did an IV analysis and the results were consistent, because it's distracting from is the message we don't know how big it is, or it's at least $3,000 big. So it's what do you sell? What do you sell to the audience? What does the audience want to hear, and what can the audience understand? And let me try and introduce this element that's really complicated, but at the end of the day, I can't tell you exactly what it's doing for you. Maybe I don't need it. I don't know. It depends on the approach to your paper. Like, and I don't know. I just don't know how much room there is for like. We did IB and propensity scores and OLS, and the contribution to our contribution is that we do it in 3 different ways, and we just want to show you that they're different. And like I hope they did it for CAP, we're doing it for drug-eluting stents. Drug-eluting stents by itself maybe not important enough to. I mean, why? Who cares? So where's the hook here? Could I get it into a cardiology journal somewhere? Probably. But maybe a fight, because the good cardiologists will be like, we don't understand it. And then the less good ones who are more desperate may also say, we don't understand it. Why are you shopping it around? And at the end of the day, I'm not with, well, I got a self-published paper. So, I mean, that goes back to the way earlier comments about what are you spending your time working on? And like, what's your expected value add? Why do you need IB? What's IB getting you? And like, this is why. So like, oh, this is our conventional wisdom. Our conventional wisdom, conventional wisdom is everyone, there's been multiple studies showing that drug-eluting stents cost $2,000 more, but they're not doing it right. They're not controlling for all this other stuff. And when we do it the right way, we get a much larger estimate. But our right way better be right and not, like, well, our instrument's pretty good, but, we're not foolish. Maybe we get a second instrument. So I don't want to scare you off of IB, because it's one of the most compelling ways to get a causal effects, and yet it's not perfect. And it's only as good, the approach is only as good as the instrument or instruments that you have. So I'm not going to go through the rest of the technical stuff because that's even more confusing. But I do want to conclude with a few comments just about things to look for in summary when you're evaluating a paper that uses IB or thinking about doing when you're